No, magnetism is an amazing subject, I think, because it's a superb example of where the standard scientific paradigm of reductionism doesn't work. You know, one atom is not magnetic. It's a cooperative effect that when you have a large number of magnetic species, that they can show this long-range order or some particular type of behaviour that is not apparent in the single atomistic unit.
So what would you? That's a quite interesting thing to say. That's not reductionistic. Someone might still think, well, but you've reduced it down to, atoms and quantum mechanics. But you're saying that's not the right way of saying. What do you mean by it's not reductionistic?
It's not reductionistic in the sense that, well, it's not atomistically reductionist. So there is a tendency in physics sometimes. If you give a physicist a complicated watch and say, how does it really work? The physicist's response is to take a large hammer and smash it to tiny smithereens and study the bits. That's what we do in our particle accelerators. And we do have this idea that is successful in lots of cases, that by smashing something to bits and studying the fundamental objects that make something up, that's the route to understanding. But in fact, quite often, that isn't the case. That when you smash your watch to bits, you just end up with a lot of bits. And you've lost whatever it is that is part of the way that watch works. And it's, yes, quantum mechanics is important, but in fact there are often higher level principles that govern the way in which magnets, for example, work. And sometimes those higher order principles also will tell you about the way that a liquid turns into a gas, or some other phase transition will occur. So these higher order principles, in some sense, they're almost independent of the microscopic species that make up the thing that you're trying to study.